In the power systems analysis field of electrical engineering, a per unit system is the expression of system quantities as fractions of a defined base unit quantity. Calculations are simplified because quantities expressed as per unit do not change when they are referred from one side of a transformer to the other. This can be a pronounced advantage in power system analysis where large numbers of transformers may be encountered. Moreover, similar types of apparatus will have the impedances lying within a narrow numerical range when expressed as a per unit fraction of the equipment rating, even if the unit size varies widely. Conversion of per unit quantities to volts, ohms, or amperes requires a knowledge of the base that the per unit quantities were referenced to. The main idea of a per unit system is to absorb large difference in absolute values into base relationships. Thus, representations of elements in the system with per unit values become more uniform. A per unit system provides units for power, voltage, current, impedance, and admittance. Except impedance and admittance, any two of these are independent and can be arbitrarily selected as base values, usually power and voltage. All quantities are specified as multiples of selected base values. For example, the base power might be the rated power of a transformer, or perhaps an arbitrarily selected power which makes power quantities in the system more convenient. The base voltage might be the nominal voltage of a bus. Different types of quantities are labeled with the same symbol. It should be clear from context whether the quantity is a voltage, current, etc. Per unit being used in power flow, short-circuit evaluation and motor starting studies, it is important for all power engineers to be familiar with the concept. Purpose: there are several reasons for using a per unit system. Similar apparatus will have similar per unit impedances and losses expressed on their own rating, regardless of their absolute size. Because of this, per unit data can be checked rapidly for gross errors. A per unit value out of normal range is worth looking into for potential errors. Manufacturers usually specify the impedance of apparatus in per unit values. Use of the constant is reduced in three-phase calculations. Per unit quantities are the same on either side of a transformer, independent of voltage level. By normalizing quantities to a common base, both hand and automatic calculations are simplified. It improves numerical stability of automatic calculation methods. Per unit data representation yields important information about relative magnitudes. The per unit system was developed to make manual analysis of power systems easier. Although power system analysis is now done by computer, results are often expressed as per unit values on a convenient system-wide base. As we have already known, the purpose of introducing per unit system is to simplify our conversion between different transformers. Hence, ALll unregistered trademark D like to illustrate the steps for finding per unit values for voltage and impedance. First, let the base power of each end of the transformers becomes the same. Once we set every S on the same base, we can get base voltage and base impedance for every transformer easily. The numbers we have till now are all based on the same unit. Next, substitute the real numbers of impedances and voltages into the per unit calculation definition. We can get the answers for per unit system. In other case, if we unregistered trademark they known the per unit values at first, we can get the real values by timing base values. Base quantities, generally base values of power and voltage are chosen. The base power may be the rating of a single piece of apparatus such as a motor or generator. If a system is being studied, the base power is usually chosen as a convenient round number such as 10 MVA or 100 MVA. The base voltage is chosen as the nominal rated voltage of the system. All other base quantities are derived from these two base quantities. Once the base power and the base voltage are chosen, the base current and the base impedance are determined by the natural laws of electrical circuits. Note the base value should only be magnitudes, while the per unit values are phasors. The phase angles of complex power, voltage, current, impedance etc. are not affected by the conversion to per unit values. As we have already known, the purpose of introducing per unit system is to simplify our conversion between different transformers. Hence, it is appropriate to illustrate the steps for finding per unit values for voltage and impedance. First, let the base power of each end of a transformer become the same. Once we set every S on the same base, we can get base voltage and base impedance for every transformer easily. The numbers we have until now are all based on the same unit. Next, substitute the real numbers of impedances and voltages into the per unit calculation definition. We can get the answers for the per unit system. In other case, if we have known the per unit values at first, we can get the real values by multiplying by the base values. By convention, we adopt the following two rules for base quantities. The value of base power is the same for the entire power system of concern. The ratio of the voltage bases on either side of a transformer is selected to be the same as the ratio of the transformer voltage ratings. With these two rules, a per unit impedance remains unchanged when referred from one side of a transformer to the other. This allows us to eliminate ideal transformer from a transformer model. Relationship between units. The relationship between units in a per unit system depends on whether the system is single-phase or three-phase. Single-phase equals, assuming that the independent base values are power and voltage, we have. Alternatively, the base value for power may be given in terms of reactive or apparent power, in which case we have, respectively. Or, the rest of the units can be derived from power and voltage using the equations, and, being represented by, we have. Three-phase equals, power and voltage are specified in the same way as single-phase systems. However, due to differences in what these terms usually represent in three-phase systems, the relationships for the derived units are different. Specifically, power is given as total power, and voltage as line-to-line voltage. In three-phase systems the equations and also hold. The apparent power now equals. Example of per unit. As an example of how per unit is used, consider a three-phase power transmission system that deals with powers of the order of 500 MW and uses a nominal voltage of 138 kV for transmission. We arbitrarily select, and use the nominal voltage 138 kV as the base voltage. We then have. If, for example, the actual voltage at one of the buses is measured to be 136 kV, we have. Per unit system formulas. The following tabulation of per unit system formulas is adapted from Beeman's Industrial Power Systems Handbook. In transformers, it can be shown that voltages, currents, and impedances in a per unit system will have the same values whether they are referred to primary or secondary of a transformer. The full load copper loss of a transformer in per unit form is equal to the per unit value of its resistance. Therefore, it may be more useful to express the resistance in per unit form as it also represents the full load copper loss. References: Beeman, Donald. Short circuit current calculating procedures. In Beeman, Donald. Industrial Power Systems Handbook. McGraw-Hill PPC ESP. 38 to €41, 52 to €55. ALll, ALll. A Section 2.5 per unit representation of impedances, currents, voltages and powers. Electric Energy Systems Theory, An Introduction. Tater McGraw-Hill pages 35 to 39. ISBN 978-0070192300. UN, Moon 8 Short Circuit ABC, learn it in an hour, use it anywhere, memorize no formula. IEEE Trans. On Industry Applications. IA 10, 261 to €272 doi, 10.1109/TIA. 1974.349143. William D., J.R., Stevenson. Elements of Power System Analysis. New York, McGraw-Hill. ISBN 0-07-061285-4. Weedy, B.M. Electric Power Systems. London. Toronto, J. Wally. ISBN 0-471-92445-8. Glover, J. Duncan. Sama, Mueller-Kutler. Overby, Thomas J. Power System Analysis and Design. Cengage Learning pages 108 to -116. ISBN 11114255779.